Okay, long time no see. We are just jumping right into the second part of things that you're going to need, or the things that you can use the alternating series for. Here we have an alternating series. I wrote it out real quick. It's the sum of -1 to the n plus 1 over 1 over n squared from 1 to infinity. Now, if someone came up to you and said, hey, what does that equal? What is it actually approaching? We know it converges conditionally. Actually, it converges absolutely. What is it approaching? And you could say, well, I don't know. I mean, I don't know either, right? I don't know the answer. But I could say, we can start figuring it out, right? So we can start figuring it out. We can come over here and say, let's start typing in some numbers. And you type in, like plug in 1. Plug in 1, you're going to get 1 times 1. Plug in 2, you're going to get -1 times 1/4 and plus 1/9 minus 1. This is going to go on forever, right? And if you wanted me to figure out the number, I'd be here forever, right? It would take me forever. But I could give you an approximation. I could say, well, I'm going to use those 4, right? I'm going to use those 4. Now, those 4 are not the actual sum of this infinite series, right? They're not the series sum, but they're a decent approximation. And if I'm going to use 4 terms, I'm going to call this S of 4 to represent the sum of 4 terms. And I'm going to get some number, and let's see, that's going to be what, 0.75 minus 16, 0.6875, I should check this with my calculator, 0.6875 plus 0.111, 0.6875 plus 111. Okay, so that's what it's going to be. That's some sum. And that sum is something that we actually don't know. By the way, that might be wrong. I'm sorry if it's wrong. But that's some number that we actually have that we can say, hey, that's a good approximation because it uses 4 of the terms. Is it the absolute infinite sum? No, it's not. So there's going to be some difference, right? There's going to be some difference between what's actually the real sum and our approximation. And that's some difference. And I put an absolute value because I don't really care what direction it's in. So this is how far we're going to be off by, right? And this is how far we're really off by. We don't know S sub infinity, but we know that's how far off we are. And it's some theoretical thing that we're off by. Now, here's the cool thing. We don't know how far off we are. We don't know how far off we are, but we know we're not that far off. Because if we think about what we did with alternate series before, I got to go back. Let me go back here. Remember what I said, like what we did previously in a video where I said we're going out 1 and then we're going back -1/2. Then we're going out a third, then we're going back in -1/4. And the reason why we knew this converged is because every single time it was getting closer and closer and closer to 0. Right? It's getting smaller and smaller. And if you think about this, if I'm off here, right? Think about it's getting smaller every time. So if I'm going to have to erase it. But say I came down to here, right? I know I'm going to go back in this direction, but I'm not going to go back as far as I was the last time. So therefore, it's going to have to be how far off I am. Say I estimated it right here while I was here. I'm not that far off. That's what I'm actually off by. And notice that I'm off. This amount here that I'm off by is less than the next term. Okay, so I know that's really ugly to see, but now let's just say I added the 1/3 in, right? Say I had the -1/2, and I added the 1/3, and now I'm here. Okay, I'm at this number right here, and okay, I'm at this nice number, whatever, 5, 6, and here I am, and now I'm going to say, well, how far off am I? Well, the green line is the true line. I don't know really where it is, but I know that I'm off by that amount, and the magnitude of this amount is less than the magnitude of the next term. Because I kind of know that the next term is going to overshoot. I know that the next term that I added, when I subtract that 1/4, I'm going too far. Then when I'm here, I'm adding the 1/5, I'm going too far. So I know that I'm off, but the amount that I'm off is actually less than the next term. So this is called the alternating series error bound. What it's saying is that you know you're off, and you know that you are off less than the next term. So you say to me, well, Mr. Popick, you said it's 0.7986111. I said, yeah, I know that I'm off. And in fact, I know that I'm too low. How do I know that I'm too low? Because next time I'm adding a positive term. Well, how far off are you? Well, the next term, a sub 5, is 1/25. So I know that while I'm off, this 0.798611, I'm off. I know that I'm off by less than 0.04. So if you said to me, hey, Mr. Popick, what's the actual sum? I could say it's 0.7986111 plus some number that is less than 0.04. so that I can kind of give you a range of values for the sum. You may say to yourself, well, that's not that useful. I'd much have, an exact number. Well, then get out a calculator and keep adding them up, right? You can do that. But this at least gives me some kind of idea of an error bound that I have. The next term is the error bound. So the next question that someone could ask you, they could say, hey, do me a favor, give me an approximation. And when you give me that approximation, make sure it's kind of less than 0.01 away. You're like, okay, you want me to be 0.01 away? I can be 0.01 away. And in order for me to be 0.01 away, I have to figure out how many terms do I need to add up, right? So the question is, how do I make sure that I'm 0.01 away? So I'm going to have some number here. And I don't know. I'm going to have some number here, right? I don't know what this number is. But this number here, I want to make sure is less than 0.01. So therefore, I want to make sure that whatever number here, whatever number I choose for n, I'm less than 0.01. So for this series, let's just say I need to figure out what term is going to make sure that some term that I have, some term in the future, a sub kind of n plus 1, I need to make sure that this number here has to be kind of relatively small. So it has to be less than or equal to 0.01. Because once I find some number that here is small enough, that a sub n plus 1 is small enough, then I know that that number, when I plug it over here, into this term, when I plug it into this, then I know that I'll be close enough, right? As long as this number here that I choose is less than or equal to 0.01, then I know that my error, how far off I am, is going to be less than 0.01. If for this scenario, I chose 0.01 for a reason, because 0.01 equals 1 over 100, which is 1 over 10 squared, which just happens to be a sub n. Sorry, I said a sub n, I meant a sub 10. And therefore, I know that I'm at least, if I came in here and said, well, I can rewrite this. So I'm rewriting this now as a sub 10, right? And therefore, I can solve for the fact, well, if that's 10, then that means if I add up the first 9 terms, if I add up the first 9 terms, why? Because 9 is 1 less than 10. If I add up the first 9 terms, which I'm not going to do right now because I just don't have my calculator handy, but if I added up, it just kept on this 0.798611 and added 1 over 25, subtracted 1 over 36 and so forth, all the way up to 1 over 81, I know that I'm going to be within 0.01 from the correct answer. And that's another question that you could be asked, right? You could be asked, how far off are you? So you use 4 terms like we did initially, and then you were asked, what's the maximum error that you're off? Or you could be asked, hey, how many terms do you need to go to in order for you to make sure that you are actually within some kind of error bound, that you're within 0.01? Okay, folks, that's it for now. I'll do a few examples. Enjoy.